Hi guys, welcome back to Data Every Day. Today we're looking at sort of an interesting data set. It's a data set of CAT scans, and it's actually features that have been extracted from images. So I'm guessing there was some sort of convolutional neural network involved, which looked at images and extracted these 384 features, which we see in these columns from value 0 all the way until value 383. Then at the end we have this reference column, which is a continuous numeric column that displays, if we see up here, it displays the relative location of the CT slice on the axial axis of the human body. So along the axial axis, where was the scan taken from? And that's what we're going to try to be predicting using these features that were extracted from the images. So let's hop into the notebook. We're going to use NumPy and Pandas for working with the data. For pre-processing, we'll use the train test split function from sklearn and the standard scaler, also from sklearn. For the model, we'll build a neural network using TensorFlow and Keras. So let's go ahead and import all of this and load in the data using pandas.readcsv. So we'll go and grab the file path to the CSV file, which is right up here. Paste that in. And let's take a look when that finishes. Here it is. This is what we saw on the other page. Now you notice we can't see all the columns here, but in this case we don't really need to, because we know exactly what we're dealing with. It actually tells us the first 241 features describe a histogram of the bone structures in the image, and so actually maybe this is not a convolutional feature extraction, because we actually know what these are. Right, so we found some way to make a histogram of the bone structures, and we also have a histogram of the air inclusions. So that's what the features are sort of made up from. We have this histogram of bone structures and this histogram of air inclusions, and we're going to try to use these together to make the predictions. So we know these are all floats because they describe a histogram, right? So if we check out data.info, we can just double check that. Yeah, and you can see we have 385 float columns and a single integer column. And this integer column is just the patient ID. So I think there's 96 patients in this data set. However, we're not going to use this because we want to build a model that can predict regardless of patient. So let's start pre-processing. So we'll create a function called preprocess inputs that's going to take in a data frame and make a copy of it. And then we'll do all of our pre-processing in this function and return the data frame. So right now it's just going to return a copy. So we pass in data to this function, get it back in x. And you can see it's just a copy right now. But the first thing I want to do is drop this column since we don't need it. So let's drop the patient ID column. And to do that, we can just do df equals df.drop patient ID from axis 1. And you can see it's no longer there. The next thing to do would be to split the reference column, which is our target column, off from the rest of the data. So let's split the data frame into x and y. So y is going to be a vector just containing our targets, which will be the reference column, so df sub reference. And x is all the rest of the data. So here it will drop reference from axis 1 and store that into x. And let's return x and y. So now if we get them back over here, x now no longer has this reference column at the end, and y is just the reference column. Alright, now we'll do our train test split. So now we want to split the data into, we'll send 70% of the data to the train set, the other 30% can be used for testing. So that we'll get x train, x test, y train, and y test. And for this we'll use the train test split function from sklearn. So we'll pass in x and y, specify our train size to be 70%, keep shuffled equals true, and give it a random state of 1 so that we can reproduce the results. And then I want to return these 4 sets of the data now, and I want to get them back over here. Let's run that and take a look at x train. So we've shuffled the data. We're also only working with 70% of the data. And y train should be the target values for each of these examples. So you can see the indices should match up there. And then the test set is just the other 30%. Okay, so there's one more step I want to do, which is to scale the data. So right now, all these columns take on various ranges of values. Just to double check this, we can look at xtrain dot describe. So I'm not sure exactly what the unit of these are, but if we look at the mean, okay, they're fairly close to 0, so that should be all right. The standard deviations, it looks sort of like they're on the same scale. Yeah, it looks like they've been min-max scaled, so the min is 0, the max is 1 in almost every column. So this might be fine. We can try this out, but I might also consider scaling with standardization, which means that let's center the data at 0, so every column has a mean of 0, and then scale it in some way so they all have the same standard deviation or variance. So let's try them both. First we'll try without scaling, and then we'll go back and scale and see if we get better results. So for now, let's just build the model. So training. And here we're going to create our input layer. That will be tf.keras.input. And the shape of this should be this. This is the shape of a single input vector coming into the model. So we can get that by looking at the shape of xtrain. And so we have 37,000 examples, and each example has 384 inputs. So the shape of a given input is 384. Then we'll create our two hidden layers. So these will be dense layers, and I'll give them both 128 neurons and a ReLU activation function. And here we'll pass in inputs, and then we'll duplicate this because we want two layers, and we'll pass in x to this one. Then we'll have our outputs, which will also be a dense layer, but it will only contain one value, which will be the actual prediction we make, that hopefully is somewhere in line with the actual value that we compare it to. And this will have a linear activation, which just means no activation. That means this value can take any range, any real number essentially. We'll pass in the x, and then we will create the model. So that's tf.keras.model, inputs equals inputs, and outputs equals outputs. Then we'll compile the model. Here we'll give it an atom optimizer. So atom. And then we'll also specify our loss function, which will be mean squared error, since this is a regression task. Once we've compiled the model, we'll just fit the model and store its results in history. That's model.fit, and we're going to train on the train set, so xtrain, ytrain, and then give it a validation split of 20%, so that we can so we'll use 20% of the train set for validation. Then we'll give it a batch size of 32. Number of epochs can be 100, because I'm going to use the early stopping callback function. That's tf.keras.callbacks.early stopping. Here this allows us to monitor a value, which let's monitor the validation loss, which is sort of a measure of when your model starts to overfit, because the validation data represents unseen data to the model. So when the validation loss starts to increase again, the model is no longer performing well on unseen data, and at that point you can conclude that the model is beginning to overfit. So what the early stopping callback does is it allows us to automatically check when the validation loss starts increasing again, and it will stop the training right there and restore the weights from the best epoch that I've trained on. And so we specify a patience value of 3. This is the number of consecutive epochs that we allow for the loss to increase. So after 3 consecutive epochs of no improvement in the validation loss, we'll stop the training and we'll restore the weights from the best epoch. So restore best weights equals true. Alright, we'll run this. And it should train very quickly because we do have a good number of training examples, but we don't have many parameters in our neural network to tune. So it will take probably just a minute or so. Yeah, it looks like the validation loss. Actually, alright, I'll pause the video and I'll return when we complete this. Alright, it completed, and you can see the loss decreased until it started, it hit a minimum and it started to increase again. And you can see this training is a little unstable. You can see it's bouncing around a little. When you see that, you may consider increasing the patience threshold to a higher value to allow for more fluctuations before concluding that your model is overfitting. But I think this is fine. We're getting a decent performance. So let's look at the results. And to understand the results, I will calculate two metrics, which will be the RMSE and the R squared. So the RMSE is the root mean squared error, and it's basically the square root of what we're seeing here. And it's basically a measure of how the average error of your model across all training examples, but in the unit of the original target variable. So let's look at y-test. This is our target variable. And so I'm not sure what this unit is actually. There's some sort of histogram values, so maybe it's just frequency, right? Okay. So if this is a frequency value. Oh, sorry, this is not frequency. This is the target variable. So it's relative location. And is this it? Values are in range of 0 to 180, where 0 denotes the top of the head, and 180 denotes the soles of the feet. Okay, so now we know the unit. It's basically just a measure of where along the body it is. So we want to know how far off are we on average. So this is on a scale of 0 to 180, and if we look at dot plot, we should be able to see this if we plot it as a histogram. Yeah, so from 0 to 180, here's the distribution of the variable. And so we're hoping if we get some sort of error, it's something small relative to this scale. So the root mean squared error is a way of understanding that on the same scale as your target variable. So let's calculate it. First, we're going to need a set of predictions. So we'll do model.predict on the test set and store those in ypred. Now if we look at ypred right now, you can see it has our predictions. However, if we look at ytest, and let's look at the shape of each one, you can see this has an extra dimension, just a dummy dimension. We don't need it, so we'll actually use numpy.squeeze to squeeze that extra dimension out. And now it will be one-dimensional. So I'm just going to use this up here so that we have our test and our predictions both one-dimensional. If we run that and then we look at ypred, you should see the shape is now one-dimensional. Alright, so we have our predictions, and we want to calculate the error between the predicted values and the real values. So let's take the real values and subtract the predicted values. And right here, these are the errors. So this is how far off we are for each example. However, if I take the mean right now, if I were to get the average error here, we'd run into a problem, which is it'll be very close to 0. And the reason is we have negatives and positives, which are going to cancel each other out. So to work around this, we square this difference element-wise, so that all the values are on the positive scale. Then we can take the mean. However, now this is the mean squared error, so we're in the squared unit of the original target variable. So now we're going to square root it again to give it back to the unit of our target variable. So this is the average error across all examples in the unit of our target variable. So that's called the RMSE, or root mean squared error. And we can print it out. And let's display it to 2 decimal places and format here with RMSE. So this is actually extremely good, right? Let's do 5 decimal places. Okay, the reason this is so good is because we're working on a scale from 0 to 180. So to get an average error of less than 1 is very good. So I'm guessing that these features that were extracted are very informative and rich in information. So the other one we can do is the R squared score, which is it's not so interpretable as this one, where this sort of is an absolute measure of how well your model is doing in respect to the target variable. The R squared score is more of a comparative metric that shows you how better your model is than another model. Now, technically, you could calculate this using any 2 models to compare, but the R squared score is specifically designed to compare your model to the baseline model. And by baseline model, I mean we take the test set. If we only had these target values available to us, if we had no x-test at all, if we couldn't really build any sort of neural network or anything, because all we had was this, the best thing we could do is to predict the mean every time. So if we just predicted this mean every single time, and we calculate the error there, so ytest minus ytest dot mean, we get some errors, and you can see there's actually much worse than our model, right? But so the R-squared score is a way of comparing how much better is our model than this. So what we can do is square these values like we did before, and then take the sum instead of the mean. Just take the sum of them, so it's the sum of squared errors for the baseline model. And we'll do the same thing for ours, so we'll just change ytest.mean to ypred, which are our predictions. So these are our sum of squared errors, and these are the baseline sum of squared errors. And we want to compare them. So what we'll do is put them in a fraction, with ours on the numerator, the baseline's on the denominator. And so when we have the same error as the baseline, this fraction will evaluate to 1. And when we have much less error than the baseline model, this fraction will approach 0. And when we have much more error than the baseline model, this fraction will approach infinity. So the R-squared score is almost this. It's this whole thing, but 1 minus it. And what that does is, when we have 0 error, 1 minus 0, well, the fraction becomes 0, and 1 minus 0 is 1. So the best R-squared score you can get is 1. On the other hand, if we have infinite error, then this whole thing goes to positive infinity, and 1 minus positive infinity becomes negative infinity. So the R-squared score takes on a range from negative infinity until 1, like that. And I guess it could technically be 1, but you're never going to get 1, because 1 would mean that your predictions are exactly the same as the actual values. And if you have the same error as the baseline model, means this fraction is 1, then 1 minus 1 is 0. So the 0 is the threshold for when your model is getting better than the baselines. Alright, let's calculate this. And we have a 0.998 R-squared, which is what I'd expect because we had such a good RMSE. This means we have a 99.8% reduction in error between the baseline model and ours. So this is very, very good. So let's print that out. We'll call this R2. And we're going to print R-squared score, display this one to 5 as well, and format using R2. Alright, and there it is. So before we go on, before we end, I just want to try this again with scaling. So we didn't scale up here, but if we did, I want to see how that affects the performance. So we create the standard scalar, which is a scalar that will give each column a mean of 0 and a variance of 1. And we can fit the scalar to the train set. And then we can transform the train set and the test set using scalar.transform. And I'll store it back into xtrain. However, this transform function returns a numpy array, so I'm going to turn it back into a data frame afterwards so that we can keep it in this format. And we'll keep the indices the same as they were, and the column names the same as they were before. Then we'll go and do the same thing for xtest. That's all we have to do. And the reason I only fit this to the train set is because we want to pretend we don't have access to the test set when we're fitting the scalar. Alright, so now you can see they should be all centered at 0 with a variance of 1 for every single column. Alright, everything else is the same though. Let's just retrain this and I'll resume the video when this completes. Alright, and it finished. It looks like we might actually be getting worse results. So let's just check this again. We're now going to recalculate the R-squared and the RMSE. And yeah, so it went up. Our RMSE went up to 1.2 as opposed to 0.87. And so it looks like there is a detectable decrease in performance when we scale using a standard scalar. Now the other thing we can do is try a min-max scalar. So like I said, this data has already been min-max scaled, as we could tell. But let me just show you. Let's not scale for a second and check out the original xtrain again. If we look at xtrain.describe, you can see that the min is always very close to 0 and the max is always very close to 1. However, they're not exactly 1. And so I assume this is because it was min-max scaled on some larger data set. Actually, I wonder if we were to use the original x, if we didn't train test split. If we return x at the end and just get that back, I want to see x.describe, because maybe that will always have a min of 0 and a max of 1. No, okay, it doesn't. Okay, so they're not exact. It's not exactly min-max scaled. However, I'm not sure if it would be better if we tried our own min-max scaling to get it perfect. So let's see if that would be better. We'll give it a min-max scaler, which if we run this now, and let's not return x anymore. You can see if we run xtrain.describe again, the mins are now always 0 and the maxes are always 1. So let's see if that's any better. So we'll run this one more time and we'll see where this takes us. Alright, it completed. So I'm not actually sure if this is how reliable this is, because like I said, it's sort of it's an unstable training. The loss is fluctuating a bit, and so it may have stopped prematurely because of the early stopping callback function. So right now we'll probably get something. It was better, but it's not quite as good as we originally had. So let me try bumping this up to 5 patience value and retraining. Alright, and that one's looking pretty good. We're getting the loss dipping down now below 1. So let's see how this goes. Alright, and it's still not as good. So it's possible, it's hard to say because there is a good deal of randomness that goes into a neural network, and with TensorFlow it's a bit hard to control that. But this was, we can almost be sure that all these values were taken in the original unit rather they're all in the same unit. And so when that's the case, you don't really need to do any scaling. And it turns out that maybe the scaling was not the best move here. So we're not going to scale. And we're just going to try to get values as close to the original ones that we got, which was really, really good. So that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.